Welcome to the sixth lecture of Module 1 on diffusion mass transfer. In this lecture, we will discuss on the diffusion coefficient measurements and its prediction. So, before going to this lecture, we will just have a recap on our previous lecture. In our previous lecture, we have discussed steady state molecular diffusion of a component through variable cross sectional area or non uniform geometries. So, in this case we have considered three cases. In first case we have considered steady state diffusion of component A through non diffusing B in a uniformly tapered geometry, triangular cross sectional area, and in the second case we have considered steady state diffusion of component A through non diffusing B from spherical geometry, and the third case we have considered uniformly tapered cylindrical geometry and equimolar counter diffusion. Equimolar counter diffusion through uniformly tapered cylindrical geometry. So, today we will discuss diffusion coefficient measurements and prediction. As we have already said when we discussed the fixed first law, we have seen that the proportionality constant for that fixed first law equation is the diffusion coefficient. So, the diffusion coefficient we can define from the fixed first law the flux divided by the concentration gradient, and unit of diffusivity is meter square per second, that is length square per time, and it is a function of temperature, pressure and concentration. For gases, the diffusivity increases inversely with the pressure, that is D of A into B is inversely proportional to pressure of the system, PT, say total pressure, and with temperature it is directly proportional. In general, T to the power 1.5, but for liquid the pressure dependence on diffusivity is negligible, and diffusion coefficient for gases varies in the range of 10 to the power. For gases, the diffusivity values varies in the range of 10 to the power minus 5 meter square per second into liquid it is around 10 to the power minus 10 to 10 to the power minus 9 meter square per second, and in case of solids, that is diffusivity of a particular gaseous components into the solids is approximately in the range of 10 to the power minus 13 to 10 to the power minus 10 meter square per second. So, today first we will consider the diffusion coefficient measurement for the gas phase. So, the liquid phase diffusion coefficient measurements will come later. There are several methods available for the diffusion coefficient measurements for the gas phase. Out of the available methods, the two simple methods we will consider for this lecture. One is very simple method is twin bulb method, and second one is Stefan tube method. And there are some empirical correlations available by which we can also predict the diffusion coefficients. And third one we will discuss for the gas phase diffusion coefficient prediction is the predictive method. From correlation. So, let us consider the first gas phase diffusivity measurement method, that is twin bulb method. In this method, the two large volume bulbs are connected with a capillary tube or narrow tube, and the volume of one bulb is V1 and volume of other bulb is V2, and they are kept at constant pressure and temperature, say Pt and T, both the bulb, and then there are three valves, valve 1 for bulb 1, valve 2 for bulb 2, and there is a valve in the capillary tube at the middle. So, initially all these three valves are open, and then this system is evacuated, and then the three valves VA1, VA2 and VAT, these are closed. Then the valve 1 VA1 is opened and filled with a pure component A, and then the valve A1 is closed, the valve A2 is opened, and then pure B is filled through VA2, and then VA2 is closed. The whole system remains at a constant temperature and pressure. Then the valve VAT is opened for a period of time, say T, and then VAT is closed, and the sampling through the sampling valve from both the bulb was taken out and analyzed for their composition. So, the assumptions over here we have taken the negligible capillary volume, the second one is each bulb is always of a uniform concentration and then pseudo steady state diffusion through the capillary This means that at any instant the diffusion through the connecting tube occurs at steady state as soon as the concentration between these two valves changed a little, a new steady state condition is maintained. So, at any instant steady state condition is maintained and the volume in this case we have considered of this capillary volume is negligible and there is suitable arrangement to keep this each valve concentration at all the times at uniform concentration. Let us consider the cross sectional area of this tube is A x and the length which is given is L and volume V 1 and V 2 and the partial pressure for valve 1 is P A 1 for component A and for component A in valve 2 is P A 2 and P A 1 is greater than P A 2 and the total pressure remains constant. Since the total pressure remains constant, equimolar counter diffusion will take place. Equimolar counter diffusion will occur, will take place. So, at steady state transport of A from valve 1 to valve 2 we can write as A x into flux of A is equal to A x diffusion coefficient A b into the partial pressure difference P A 1 minus P A 2 divided by R T L which will be equal to minus A x N B. So, this is equation number 6.1. Now, at any times if we assume the gases are ideal gas, in that case we can write at any time t minus V 1 by R T d P A 1 dt will be equal to A x N A 6.2 and V 2 by R T d P A 2 dt will be A x N A. The negative sign in equation 6.2 indicates that the partial pressure is decreasing with time, whereas in valve 2 the partial pressure of component 1 is increasing in valve 2. The partial pressure of A in valve 1 is decreasing with time, whereas the same component is increasing with time in bulb 2 because of diffusion from higher partial pressure to the lower partial pressure. If we sum these two equations 6.2 and 6.3, we will have minus d P A 1 minus P A 2 dt will be equal to A x N A R T 1 by V 1 plus 1 by V 2. This is equation number 6.4. Now, if we substitute this relations A x N A in place of this term, so we will have minus d P A 1 minus P A 2 dt will be equal to A x d A B P A 1 minus P A 2 divided by L into 1 by V 1 plus 1 by V 2. So, this is equation number 6.5. Now, if we use the following conditions at t is equal to 0, P A 1 minus P A 2. So, initially this partial pressure in bulb 2 of component A is 0. So, this will be equal to P T, the total pressure, partial pressure will be equal to the total pressure minus 0. So, is equal to P T, and at t is equal to T, would be equal to P A 1 T minus P A 2 T. So, with these conditions, if we integrate this equation 6.5, so we will have the relation ln P T by P A 1 T minus P A 2 T will be equal to A x d A B by L 1 by V 1 plus 1 by V 2 into T. So, equation number 6.6. So, from these equations we can determine the diffusion coefficient of component A. So, in this case the parameters we need to measure is initial pressure in the vessel, second the partial pressure of one of the component, the partial pressure of one of the component in the vessel at the end of experiment. And the third thing, the time of experiment. With these parameters, we can be able to find out the mutual diffusivities from equation 6.6. Let us consider a simple example to measure the diffusivities from these experiments. To measure the diffusivity of CO2 by two valve method, the pure CO2 and nitrogen is filled in valve 1 and valve 2 respectively. The volume of valve 1 is 4 liter and valve 2 is 3 liters. These two valves are connected by a capillary tube of 5 centimeter length, 2 centimeter internal diameter. The partial pressure of CO2 in the valves 1 and 2 are 60 kilopascal and 40 kilopascal respectively at the end of 6 hours. The valves are maintained at 100 kilopascal pressure and 313 Kelvin temperature. Calculate the diffusivity of CO2. Let us write down the parameters which are given. The volume of the two valves, one valve VA1 is 4 liter, V2 is 3 liter, and length of the capillary tube is given, which is 5 centimeter, and the ID internal diameter of the tube ID is 2 centimeter, length is 5 centimeter. Total pressure PT is 100 kilopascal. Partial pressure 1 is 60 kilopascal. PA2 is 40 kilopascal. And time T is 6 hours. So, these are the parameters which are given. So, now L, the volume which is given is, we can write it is 0.004 meter cube, and this is 0.003 meter cube, and this length is 0.05 meter, and then from this we can calculate cross sectional area, which is pi d square by 4, which will be equal to pi 2 into 10 to the power minus 2 meter whole square by 4, and it will be 3.14 into 10 to the power minus 4 meter square. So, this is the cross sectional area, and time we can convert into seconds. So, it will be 6 into 60 into 60. So, it will be 21600 seconds. If we replace in the governing equations, which is ln Pt by Pa1 T minus Pa2 T is equal to Ax dAb by L into 1 by V1 plus 1 by V2 into T, or we can write dAb will be equal to L V1 V2 by Ax T V1 plus V2 ln Pt by Pa1 T minus Pa2 T. If we substitute these values, so dAb will be 0.05 meter into 0.004 meter cube into 0.003 meter cube divided by 3.14 into 10 to the power minus 4 meter square into 21600 second into the sum of volumes 0.004 plus 0.003 meter cube ln 100 kilopascal divided by 60 kilopascal minus 40 kilopascal. So, this will be 2.0 into 10 to the power minus 5 meter square per second. So, let us consider another method for gas phase diffusion coefficient measurements, that is Stefan tube method. In this method, a narrow vertical tube which is connected with a horizontal tube of larger diameters. The diameter of this horizontal tube is much higher compared to the vertical tube, and in this vertical tube, narrow tube, we used to take a volatile liquid A, and this volatile liquid at the top of the volatile surface, which is say at time t, the height from the top is h, height from the top of the vertical tube is h, and the partial pressure at the surface is Pa1, which is the vapor pressure of the volatile liquids. Here we have assumed the component B, which is flowing through the vertical tube, is insoluble in the volatile liquids, that is component B is non-diffusing into component A, and component A is diffusing through non-diffusing B, and the partial pressure at the top of the surface is considered Pa2 is always 0 because of the high flow rate of component B. The liquid level from the top will drop slowly, and always there is a pseudo steady state condition is maintained. That means, as soon as some liquid or volatile liquid evaporates, and in every instance the another steady state is reached and the pseudo steady state condition is maintained. The liquid in the vertical tube usually maintained at constant temperature, and the diffusion takes place. At any time t, we can write steady state flux of A, diffusion flux of A through non-diffusing B can be written as Na dAB Pt by RTH Pa1 minus Pa2 by PBLM, where PBLM is the log mean pressure difference, which is PB2 minus PB1 divided by ln PB2 by PB1, which is equal to Pa1 minus P A 2 by ln P T minus P A 2 by P T minus P A 1. So, this is equation 6.7. Now, if we assume unit cross sectional area, that is 1 meter square cross sectional area, and dH meter of level drops in dt second. So, in that case we can write the moles transfer rho A dH into 1 divided by m A. This will be the moles of A that has been transferred or diffused. K mole of A has been left from the liquid and diffused. So, in this case we can write flux into area will be equal to K mole A transfer per time. So, if we substitute flux is N A and consider unit cross sectional area 1 will be equal to mole transfer rho A is the density of component A into dH is the level into the cross sectional area divided by the molecular weight into dt. So, this is the flux equation, mole balance equation. So, 6.8. Now, if we use the conditions following condition and integrate this equation at the first conditions at t is equal to 0, h is equal to h 0, and the second conditions at t is equal to t, h is equal to h f, t is equal to t f say. So, with these conditions and if we integrate equation 6.8, we will have rho A by m A integral h 0 to h f h dH will be equal to dAB PT by RT PA 1 minus PA 2 by PBLM integral 0 to TF dt. So, this is equation number 6.9. So, after integration we will obtain TF will be rho A H f square minus H 0 square R T P B L M by twice M A D A B P T P A 1 minus P A 2. or we can write DAB will be equal to RT PBLM HF square minus H0 square divided by twice PT MA PA1 minus PA2 into TF. So, as we said, in this case we can consider PA2 will be 0 all the times, because there is a high flow rate of air through the or component B, non diffusing B through the horizontal tube, and the partial pressure PA1 will be equal to the vapor pressure, since it is a volatile liquid at that conditions. So, let us consider a simple example to calculate the diffusivity using Stefan tube method. To measure the diffusivity of water vapor by Stefan tube method, the water is filled in the vertical narrow glass tube and held at constant temperature of 30 degree centigrade. The air is flowing through the horizontal tube at a total pressure of 1 atmosphere and the temperature is 30 degree centigrade. Initially, the water level was at a distance of 1 centimeter from the top of the vertical tube, and after 30 minutes the level drops to 1.2 centimeter from top. The vapor pressure of water at 30 degree centigrade is approximately 4.5 kilopascal. Calculate the diffusivity of water vapor. Let us write down the parameters which are given in this examples. So, given T is 30 degree centigrade, which is 273 plus 30 is 303 Kelvin. R is known to us 8314 meter cube Pascal K mole Kelvin. PT total pressure is 1 atmosphere, which is equal to 101.3 into 10 to the power 3 Pascal. PA1 is given 4.5 kilopascal, which is 4.5 into 10 to the power 3 Pascal. PA2, which is equal to 0. Molecular weight of water is 18, H0 is 1 centimeter, which is 0.01 meter, HF is 1.2 centimeter, which is 0.012 meter, TF is 30 minutes, which is 30 into 60, 1800 seconds. Now, calculate PB1 is PT minus PA1 is equal to 101.3 minus 4.5 into 10 to the power 3 Pascal, which is equal to 96.8 into 10 to the power 3 Pascal. PB2 is PT minus PA2 is equal to 101.3 minus 0 10 to the power 3 Pascal. is equal to 101.3 into 10 to the power 3 Pascal. So, PBLM we can calculate is PB2 minus PB1 by ln PB2 by PB1. Putting this value will be 4.5 into 10 to the power 3 Pascal divided by ln 101.3 into 10 to the power 3 Pascal divided by 96.8 into 10 to the power 3 Pascal. So, this will be equal to 0.99 into 10 to the power 5 Pascal, which we can write 10 to the power 5 Pascal. Now, if we substitute in this equation, DAB is equal to RT PBLM divided by twice PT MA HF square minus H0 square divided by PA1 minus PA2 into TF. So, if we substitute these values, this will be 8314 into 303 into 10 to the power 5 into 0.012 square minus 0.01 square divided by 2 into 101.3 into 10 to the power 3 into 18 into the partial pressure difference, which is 4.5 into 10 to the power 3 into the total time 1800 seconds. So, this will give around 3.4 into 10 to the power minus 5 meter square per second. So, this is the value of diffusion coefficient of water vapor by using the Stefan tube method. So, this is end of lecture 6, and in the next lecture we will continue with the gas phase diffusion coefficient predictions by empirical methods, and then we will consider the experimental determination of the liquid phase diffusion coefficients.